This video we're going to talk about the Wronskian. The Wronskian is the determinant of a certain matrix, and it can be used to see if certain functions are linearly independent on an interval. So here's the setup. Suppose that you have an interval and you have some functions, say f1 of x, f2 of x, all the way to f sub k of x are defined and differentiable k minus 1 times. In order to be differentiable, it needs to be defined. So we can probably just say are differentiable k minus 1 times on the interval which is the collection of x satisfying x's between a and b. So let's just remind ourselves that's just the closed interval from a to b. And at the endpoints, we just mean it's left and right differentiable. So right differentiable at point A and then left differentiable at point B. It doesn't really matter. Or you could just look at the open interval from A to B. So the Wronskian of the set of functions, so of the set f1 to fk, is the determinant w of x, which is the determinant of this matrix. So you take f1 and, f1 of x, and then f2 of x all the way to fk of x. So there are k columns. And then you take the derivative. So you take the first derivative, and then you take the second derivative. And basically, as you go down, you take derivatives of the function above. So for the third row, you would take the derivative of f1 prime. Well, that would be the second derivative. And you just keep taking second derivatives. That's the third row. And you just keep going. So it's like ... until you get to the last one, which is the k minus 1 derivative. K minus 1 th, k minus 1th derivative of each function. So f2 and then the k minus 1th derivative of that, all the way to the k minus 1th derivative of f sub k. And so this is a n by n matrix that you're calculating the determinant of. The Wronskian is the name of the determinant. So remember that these bars mean the determinant of the matrix, and you get rid of the brackets or the parentheses when you're writing the determinant notation. So the theorem is that, so suppose that you have these functions and you have this interval. So this is a function of x, right? Because the different x's give you, sorry, was that the, give me 1 second. Sorry, that was the mailman. So the different x's give you different determinants. So it's a function of x. So basically what's going on is for each x, you get a matrix, and then you take the determinant. So you have a Wronskian function, basically. And if the theorem is that if there is a point in the interval, some value of x, say x naught, in the interval, such that the Wronskian evaluated x naught is not 0, then the functions f1 to fk are independent. on that interval. Let's prove this, and then we'll make some comments on it. So the proof is, well, so suppose that there is some x naught in the interval such that w of x naught is not 0. We want to show that the set is independent. So what we need to do is suppose that C1 to CK are numbers, real numbers, such that C1 F1 plus dot 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 plus CK FK is identically 0 on the interval. So we want to show that C1 to CK are all 0. Okay. Well, so we have this equation, and we want to show that C1 through CK are all 0. By the way, the 3 equal signs just means, it just emphasizes that it is 0 on the entire interval. Of course, since I wrote on the interval, I don't have to use the 3 bars. It'd be okay if I just had 2 bars, but the 3 bars are for emphasis. All right, now we differentiate. So we have these functions that we can differentiate k minus 1 times. So differentiating the equation star k minus 1 times, in other words, we take the derivative of each side k minus 1 times, we get, well, what do you get when you, well, first of all, we just have C1 F1 of x plus dot 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 plus CK F K of x is 0. That's the first equation. That's the start equation. When you take the derivative, you get C1 F1 prime of x plus dot 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 plus CK Fk prime of x equals 0. And then you just keep going until you get C1 F1 to the k minus 1th derivative plus dot 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 plus CK F sub k minus 1th derivative x equals 0. Now the key is to think of this, so we have a homogeneous system of equations. And if it helps to write this, it might help to write this as, if this matrix F1 of x to Fk of x, and then F1 prime of x to Fk prime of x, all the way to the k minus 1th derivative, k minus 1th derivative of x, of f sub k. This matrix times C1 to CK is the 0 vector. I'm just writing the system of equations as a matrix vector equation. Well, so the way we've written it is this matrix is a function of x, right? This matrix here is a function of x. But now, before we didn't even mention x naught. Now we can bring in that there is some x naught such that w of x naught is not 0. So plug in x naught into this equation. We get f1 of x naught, fk of x naught, f1 prime of x naught, fk prime of x naught, all the way to f1 k minus 1th derivative at x naught, k minus 1th derivative of fk evaluated at x naught. So now we have a matrix of numbers because x naught is a number. So now we just have a matrix of numbers, and then times C1 to CK is the 0 vector. Well, we know that this Wronskian, the Wronskian is the determinant of this matrix. So since W of x naught is not 0, this matrix is invertible, right? Because you have this is a square matrix whose determinant is not 0. We know that that is equivalent to being an invertible matrix. Well, when you have an invertible matrix, so you have this matrix times the vector x is the 0 vector, what does that tell you? That tells you that x is the 0 vector. That is, well, that's the 0 vector. C1 up to ck are all 0. And that's the proof. Okay. So let's take a look at an example show that the functions one x and x squared are independent on the interval from 0 to 1. Well, we can use the Wronskian. So if you look at the Wronskian, that's the determinant of this matrix. So you have your constant function 1, so that's your f1, and then your f2, and then your f3. Then you take the first derivative, so you get 0, 1, 2x, and then you take the derivative of those, you get 0, 0, 2. And notice that the determinant is just, this is an upper triangular matrix, so it's 1 times 1 times 2, which is 2, which is not 0. So 1x and x squared are independent, linearly independent. And in fact, in general, you can show that for any k, 1x, x squared up to x to the k are independent. It's the same idea. It turns out that this Wronskian will be an upper triangular matrix, and you can get some formula, and it's not going to be 0. One thing I should mention is that the converse is not true. So it's not true that the Wronskian has to be non-zero at some place in order for the functions to be independent. So you could have independent functions where the Wronskian is just 0. So for example, so a remark is that the converse of the theorem above is not true. But it takes some experimenting and playing around to find a function that works. So for example, you could take the interval from -1 to 1, and consider these two functions, f of x, which is 0 from -1 to 0, and x squared from 0 to 1. Okay, this function is differentiable because we can see that, okay, it's differentiable to the left of 0, it's differentiable to the right of 0, and then at 0, it's differentiable because the derivative of x squared is 2x, which is 0 at x equals 0. And similarly, g of x, we define it to be x squared from -1 to 0, and 0 from 0 to 1. And g is differentiable at the same time, for the same reason. Okay, g is differentiable in the interval. But when you take the Wronskian, see, the Wronskian is more complicated because what you get, the matrix you get, depends on whether x is between -1 and 0, and 0 and 1. So if x is between -1 and 0, then you have, okay, your f is 0 and your g is x squared, and then the derivative is 0 to x, so the determinant is 0. And if x is between 0 and 1, then your f is x squared, your g is 0, and then when you take derivatives, you get 2x and 0, and the determinant is also 0. So the Wronskian is actually 0 on all of -1 to 0. Okay, so w of x is equal to 0 in the interval, but the functions are independent. Because remember, when you have two functions, they're independent if they're not scalar multiples of each other. And these functions are definitely not scalar multiples of each other. Your f is just, your f is 0 and then x squared. Right, so that's your f. And then your g is x squared to the left of 0 and then 0 to the right. So this is your f, and that's your g. Obviously, these are not scalar multiples of each other, so the functions are independent, even though the Wronskian is 0. So you have to be a little bit careful. This theorem gives you a condition that's sufficient. So if you know that there's some x naught such that the Wronskian is not 0, okay, that implies that the functions are independent, but it's not a necessary condition. It doesn't have to be the case that the Wronskian is not 0 at some point in order for the functions to be independent. But I think in practice, you rarely see this case where the functions are independent even though the Wronskian is 0. So basically, okay, it's true that it's not foolproof. I mean, in the sense that you can't always tell if functions are independent by only using the Wronskian. But it's very useful in most cases. In most cases, the Wronskian will not be 0, and so then you can conclude that the functions are independent. Okay, thanks.